Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 12, Gravitation Video 1. Today's topic is Newton's Law of Gravitation. The objectives are: know the force of gravitation is universal, know how the value of capital G was determined, to understand gravitational force on two bodies are action-reaction pairs, to understand capital G and lowercase g are two different gravitational quantities, to be able to calculate gravitational force that any two bodies exert on each other. Newton's law of gravitation states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. So Fg equals capital G m1 m2 over r squared. This is also called the inverse square law. So any two particles attract each other. That makes the law universal. Even these attractions are action-reaction forces acting on two different bodies, has the same magnitude and in opposite direction. Even if the particles have very different masses, the gravitational force they exert on each other are equal in strength. So there is a difference between capital G and lowercase g. Lowercase g is the acceleration due to gravity, which relates the weight to its mass. W equals mg. The value of lowercase g is different at different locations on Earth's surface and on the surface of different planets. Capital G, on the other hand, relates to gravitational force between any two bodies, to their masses and the distance between them. Capital G is universal constant. It doesn't change, it never changes, because it has the same value for any two bodies, no matter where in space they are located. Gravitation is spherically symmetrical bodies. So gravitational force between any two spherically symmetric masses m1 and m2 is the same as if we concentrated all the mass of each sphere at the sphere's center. So if we model the Earth as a spherically symmetric body with mass me, the force it exerts on a particle or a spherically symmetric body with mass m at a distance r between the center is this: Fg equals to Gme times m over r squared. R is the distance between the center. This is only true if the body lies outside Earth. So a force of the same magnitude is exerted on the Earth by the body also. So this means the force between the Earth and Sun doesn't depend on the size of the Earth or the size of the Sun. Now, moons, planets, and stars are all tend to be spherical. Why is that? This is because all particles in a body attract each other gravitationally. So the particles tend to move to minimize the distance between them. As a result, the body naturally tends to assume a spherical shape, because in that shape, the distance is minimal. Now, when Newton stated the law of gravitation, he states the relationship. The proportion constant was capital G was only determined over 100 years later by Lord Cavendish. So Henry Cavendish, how did he found this? He built a torsion balance, and he used that to measure G. So here's a torsion balance. So here is a bigger mass and smaller mass attached to the quartz fiber. So gravitational pull pulls the small mass toward the large mass, causing the vertical quartz fiber to twist. How much is the twist? So he shines the laser light. At that time, there is obviously no laser, but he shined the light on the mirror, and because the torsion, the quartz fiber twisted, so the reflect light is in a different direction. So he was able to measure the angle. By measuring this angle, he could measure the torque. And from the torque, he could measure the force. And therefore, he calculated capital G, or universal constant, or proportionality constant, is 6.67 times 10 to the negative 11. Now let's calculate gravitational force example. Mass m1 of the small sphere of the Cavendish balance is 0.01 kilograms. The mass m2 of the larger sphere is 0.5 kilograms. And the center-to-center distance between the two spheres is 0.05 meters. What is gravitational force on each sphere due to the nearest other sphere? Well, according to Newton's law of gravitation, Fg equals gm1 m2 over r squared. We plug everything in, and we get 1.33 times 10 to the negative 10 newtons. So as you can see, this force is very, very small, as we expected, because we don't really experience noticeable gravitational pull from the ordinary low mass objects in our environment, because this gravitational constant is very, very small. It takes a truly massive object, such as the Earth, to exert a substantial gravitational force. Acceleration due to gravitational attraction. Example, suppose the large sphere and small sphere were detached and placed in outer space, far removed from all other bodies. What is the acceleration of each? We already know the two spheres placed the same distance apart have attraction force of 1.33 times 10 to the negative 10 newtons. To find acceleration, we use Fg over m. This is the acceleration of the small body. Here's the acceleration of the bigger body. So we can see the larger sphere has 50 times the smaller mass of the smaller one, and hence its acceleration is 50 times smaller than the small object's acceleration. Note one thing is this acceleration is not constant. It is only at that instant when the two masses are 0.05 meters apart. Because there is a force, the mass is going to move close to each other. So gravitational force increases as the sphere moves toward each other. Therefore, acceleration also increases. Here is the superposition of gravitational force. Superposition means addition of vectors in this case. So many stars in the sky are actually systems of two or more stars held together by their mutual gravitational attraction. The figure shows a three-star system at the instant when the stars are at the vertices of 45-degree right triangle. Find the magnitude and direction of the total gravitational force exerted on a small star by the two large ones. So let's see, what is F1? F1 equals G m1 small mass times large mass times r squared. This r is the hypotenuse, so it's 2 times 10 to the 12 squared plus another 2 times 10 to the 12 squared. And you have 6.67 times 10 to the 25 newtons. To find the force by the lower star, we use the same thing, except in this case, the distance between the two is just 2 times 10 to the 12 meters squared. So this force is bigger because the distance is smaller. Now, these are the two vectors. To add vectors, we have to add components. Find F1x and F1y. Similarly, we have F2x and F2y. According to our coordinate system, F2x is 1.33 times 10 to the 26, and F2y is 0. So we have to find Fx, add all the x component and add all the y components. Then we use Pythagorean theorem to find resultant force and the direction of the resultants. So as you can see, the total force F on the smaller star is tremendous. It's 1.87 times 10 to the 26 newtons. The magnitude of resulting acceleration is not, though. It's F over m because the mass is so big, so the acceleration is 1.87 times 10 to the negative 4 meters per second squared. And it is not directed toward the center of the mass of larger stars. It's not the center. Center should be right in the middle. It's toward the lower end. That is because the lower star has more attraction on the smaller star than the top star. Gravitational force are important. Gravitational force are negligible between ordinary household-sized objects, but very substantial between objects that are the sizes of stars. In fact, gravitational force is the most important force on the scale of planets, stars, and the galaxies. It is responsible for holding our Earth together and for keeping the planets in orbit about the Sun. Gravitational force is so important on the cosmic scale because it acts as a distance without any direct contact between the bodies. So our solar system is part of a spiral galaxy like this one, which contains roughly 10 to the 11 stars as well as gas, dust, and other matters. The entire assemblage is held together by mutual gravitational attraction of all the matters in galaxy. So without this mutual attraction, the galaxy is not going to exist like this. Check your understanding. So the planet Saturn has about 100 times the mass of the Earth and is about 10 times further from the Sun than Earth is. Compared to the acceleration of the Earth caused by the Sun's gravitational pull, how great is the acceleration of Saturn due to Sun's gravitation? Let's see. Acceleration is Fg over me on Earth, so it's gm of Sun divided by the distance between the Earth and Sun. So as you can see, the gravitational acceleration of Earth has nothing to do with the mass of the Earth. So it only has to do with how far is the Earth from the Sun. So we don't really have to talk about mass. Let's just talk about the distance. So the Saturn is 10 times further from the Sun than Earth is. So on the bottom, R is increased by 10 times. So then the G has to be decreased by 100 times. So it's 1 over 100 as great. Okay, that's it. That's it for today. Thanks for watching. See you next time.